You type import at the top of a JavaScript file, expecting the engine to simply grab the code from another file and make it available. Instead, the process abruptly halts. Node.js throws a fatal error in the console: cannot use import statement outside a module. An import declaration triggers a different engine process than a standard function call, like require. This error marks the conflict between CommonJS, Node's legacy standard for server-side code, and the modern ECMAScript module standard used in the browser. Since the release of ES6 in 2015, JavaScript has transitioned from a scripting tool into a general-purpose language suitable for large-scale software engineering. Resolving this error requires understanding how the V8 engine maps your entire program and allocates memory before the first line of code ever runs. In early browser environments, all scripts shared a single global namespace. A variable declared in one file could be silently overwritten by a script loaded 3D tags later. To create isolation, developers used immediately invoked function expressions, leveraging closures to wrap code in a private scope and prevent global pollution. Node.js solved this by adopting CommonJS, where every file is an independent module by default. It introduced the require function to load these modules synchronously from a local disk. Browsers eventually adopted their own standard, ESM, designed for asynchronous loading over high-latency networks rather than immediate server-side disk access. The syntax error occurs when the engine attempts to apply a synchronous server-side runtime logic to a static browser-native architecture. In CommonJS, require is a regular JavaScript function. The engine executes it dynamically during the runtime phase of the program. As the engine reads a file from top to bottom, it stops and blocks the call stack every time it hits a require statement, waiting for the external file to be read from the disk. This dynamic nature allows you to put a require call inside an if statement, a loop, or even a function that only runs under specific conditions. CommonJS exports an object through module.exports. When another file imports it, it receives a static copy of that object's value at the time of the call. If the internal state of the exported module changes later, the importing file will never see the update. It is locked into a value copy. Synchronous execution works on a server, but it creates a bottleneck on the web. A single blocked call stack while waiting for a network request would freeze the entire user interface. CommonJS was built for server-side simplicity. Its blocking, dynamic design is technically incompatible with the requirements of high-performance browser architecture. ECMAScript modules utilize a structural keyword, import, which signals the engine to begin a multi-phase mapping process before execution. This is known as static analysis. The engine builds a map of the entire program without executing any application logic. Phase 1, construction. The engine builds a directed acyclic graph, a blueprint connecting all modules. Phase 2, instantiation. It allocates memory and wires imports to exact addresses. Finally, Phase 3, evaluation. The engine runs the code to fill those pre-allocated memory slots with data. Because the engine must map these memory slots before running the code, you cannot hide an import inside a conditional if statement or a loop. ESM shifts the complexity from the runtime to the compile time analysis, ensuring the application structure is sound before it boots. ESM uses live bindings rather than value copies. Since the importer points to the same memory address as the exporter, any update to a value in the source module is instantly reflected in every file that imported it. This static, pre-mapped structure enables a vital optimization, tree shaking. Bundlers like Vite or Webpack analyze the module graph. Because every export and import is explicitly defined before execution, the tool can identify exactly which parts of a library are never actually used. The bundler then methodically strips out all of this dead code before the final application is sent to the user. Removing this excess code reduces the JavaScript payload, directly improving core web vitals like largest contentful paint and total interactivity speed. The strict rules governing ESM syntax are required to ship optimized, lean code at a production scale. Pure static analysis requires the engine to download and modify the entire program upfront, which can slow down the initial page load for large applications. A user on a landing page does not need to download the code for a complex charting library until they actually click a button to view a report. The dynamic import operator acts as a compromise between static mapping and runtime flexibility. It functions like an operator triggered inside an event listener. When called, it initiates an asynchronous network request to load a module on demand. Because this process is asynchronous, it returns a promise, requiring the developer to manage the loading state and handle potential network failures. Bundlers interpret these dynamic calls as code split boundaries, automatically creating separate files that remain on the server until the user requests them. Dynamic imports provide the runtime flexibility of CommonJS without breaking the underlying ESM memory architecture. JavaScript now uses two distinct systems: CommonJS for synchronous server-side value copies and ESM for asynchronous browser-native live bindings. Node.js manages this by checking file extensions like .mjs or the type flag in package.json. These queues tell the engine which parser to initialize. The opening syntax error was the engine enforcing these boundaries, preventing developers from dropping a server-side execution model into a static network graph. Designing systems at scale requires an understanding of how these two systems handle memory allocation and execution order. The core of front-end system design involves deciding when to map code up front for safety and when to defer it to runtime for speed. Mastering the module system gives you direct control over the engine's memory management and the execution pipeline.